rotational kinematics. Does anybody know what the difference is between kinematics and dynamics? So, kinematics is the study of the description of motion without regard for its causes. Dynamics is the study of motion where you relate the motion to its cause. In other words, it's the study of forces. And now it's not just the study of forces, it's the study of torques. So we're going to be studying how torques relate to the motion of an object, how the torque on it relates to its motion. And so to start off, I want to ask you guys a little question here. So I've got a solid disk and I've got a ring. And they both are calibrated so they have the exact same mass. The ring and the disk have the same mass, and you can see they have the same radius, they're the same size. And so what I'm going to do is roll them down this ramp. And I want you guys to predict which one do you think is going to reach the bottom of the ramp first. Is it going to be the ring, the disc, or do they reach the bottom at the same time?
Both have the same weight, right?
It is.
Both have the exact same mass, same weight, same radius, same everything. The only difference is that one of them is in the shape of a ring, one of them is in the shape of a solid disc.
They're both going to reach the bottom at the same time.
The hollow one first. I heard somebody say the hollow one first. I heard somebody say at the same time.
Should reach the same time.
Raise your hand, guys, if you think same time. Raise your hand if you think they're going to reach the same time. 1, 2, 3, 4, 5, 6, 7. Raise your hand if you think that the ring is going to win. 1, 2, 3, 4, 5, 6, 7, 8. All right, 8 people think the ring. And then raise your hand if you think the disc is going to win.
You know what?
There we go. We got 1, 2, yes. 2 people betting on the disc. All right. So, guys, assuming I don't mess this up, we're going to see. So I had 7 people say same time, 8 people said disc, and then I had 2 brave people. No, so 8 people said ring. And 2 of you braver people said the disc. So let's see what happens here. Assuming I don't mess this up. The trick is I got to get this meter stick out of the way without bumping them at all.
Let's go! Yes! Yes!
See, you guys should have
Look at
done
us.
it. All right, let's check one more time, make sure I didn't screw it up. So, you got the solid disc and the ring.
Why entire solid?
Disc wins again.
Show them something.
So what is going on? Guys, same exact mass. They're the same shape, right? They're round. The only difference is that for the ring, the mass is like all around the edge. So why is it that the ring is winning the race?
The disc is right.
What do we think? Anybody have a guess?
I got nothing.
Nothing. Okay, let's figure it out. Let's go through these notes and see if we can figure out why the disc is winning the race.
I think we're about to find out.
Guys, the objective here, by the end, you should be able to relate the angular acceleration of the object to the torque applied to it. You should know how to define something called the moment of inertia. And you should be able to compare the moment of inertia of 2 objects. So that's what we're shooting for here. And really, our real objective is to explain why the disk wins. So does anybody remember Newton's first law of motion?
Bless you.
Yes. What does it
Bless
say?
you.
What is Newton's first law?
Somewhere.
Can I phone a friend? Phone a friend, yep.
Alright.
I can be, you can phone Mr. Jones. Newton's first law, it says an object will, with constant velocity, or an object will move with constant velocity in the absence of a net force. No net force means no acceleration. That's Newton's first law of motion. Anybody want to venture a guess at what Newton's first rotational version of Newton's first law is? What would be Newton's first law for rotation? Yes?
Constant
Yes.
rotation.
An object will rotate with a constant angular velocity in the absence of.
Torque. Hey, torque me up.
So we've been using this already, guys. An object will rotate with constant angular velocity in the absence of a net torque. We've already been using this, right? That is static equilibrium. Remember, 0 is a constant velocity. An object can be stationary and not moving. That counts as a constant velocity. So we've been using that when we balance objects. They have 0 angular velocity or 0 angular acceleration, I should say. So that means they have no net torque. Okay, so does anybody remember Newton's second law?
It was.
Yes. So for linear motion, Newton's second law, or I'm going to rearrange the equation you just said. Newton's second law says acceleration is force divided by mass. Same thing as you just said, I just rearranged it. That's Newton's second law. His second law says, what about when there is a net force? In that case, the velocity is not constant. The object will accelerate, and the acceleration is proportional to the net force. A bigger net force means a bigger acceleration, and it's inversely proportional to the mass, meaning a bigger mass would produce a smaller acceleration with the same force. So that's his second law for linear motion. What do you guys think his second law for rotation might be?
Angular acceleration.
You said angular acceleration equals net torque divided by what? Mass. Good, okay. So, you did the same thing you did with the first law. You swapped in all the rotational values for the linear ones. The only one that I want to ask you guys, do you think there's a rotational version of mass? Because there's a rotational version of acceleration, that's alpha. There's a rotational version of force, that's torque. But is there a rotational version of mass?
I'm sure. We're about to find out.
We're about to find out. But what do you feel in your heart? Yes or no?
Pressure.
I feel yes.
You feel like yes. It turns out that yes, there is.
Oh, I knew it.
And we use the letter capital I.
Lucky.
Alpha equals net torque divided by I. I is like mass, but it's for rotation. It's not quite exactly the same thing as mass.
Oh, that's true.
It plays the same role, though, in his laws as mass plays for his linear laws.
I thought I was current.
Eye is ugly.
Capital I think, is for inertia.
You gotta look at his engineering notes.
Oh, yeah, it's both. It's current and rotational inertia.
It's current and rotation. Yeah, that's right.
Wow. That's crazy. I didn't know one thing could be two.
It's tragic.
That's only so long.
Well, they also use M for something else too. M is used for the magnetic moment of a dipole.
Moment. You chemistry. You know, take a picture for the boys.
Okay, so guys, again, I want to stress
It's not
everything
recording.
in rotation is analogous to what you already learned for linear motion. It's all the same ideas. The challenge for you guys is going to be identifying the new variables when you read a word problem. What phrase corresponds to which variable? So let's look at an example. Well, actually, let me do a quick check before we do any examples. Guys, which of the following four cases does the bar have the greatest angular acceleration? Case A, B, C, or D? All right, let's see your answers, guys. Okay, we have almost a consensus that it is answer choice A. And that is correct.
Oh.
Can somebody explain why it is not answer choice D?
Because since it's closer to the pivot point, that second force, it's like less.
A little bit less torque.
Yeah.
So like, if this force was applied at the end, then it would be identical to case.
Yeah.
But since it's a little closer to the pivot, it's just a little bit less torque.
Mhm.
Okay. So guys, you all implicitly did what I was hoping you were going to do, which is to determine which one has the greatest angular acceleration. You just decided which one has the greatest torque. And that's all you have to do. The greatest torque is the greatest angular acceleration. So let's talk about that I in the equation. What in the world is that? So the I is called rotational inertia. You might also see it called the moment of inertia. I prefer rotational inertia, but some textbooks use moment. And I is the rotational equivalent of mass. It serves the same purpose for rotation that mass does for linear motion. More mass means it's more resistant to linear acceleration. More rotational inertia means it's more resistant to angular acceleration. It has ugly units. The units are kilograms times square meters.
Lord.
And I'll show you guys a formula at the very end of this presentation that'll show you why it has those units. And I believe, technically speaking, anybody that calls it the moment of inertia is actually not using the correct word. It's technically the second moment of inertia. The first moment of inertia is called the center of mass, and the 0th moment of inertia is called mass. So this is actually the second moment of inertia. Not that it matters, but.
Hold on.
So now we can do an example problem. So a wheel that has a rotational inertia of 10 kilograms square meters is turning around an axle that has a radius of 0.01 meters. If the wheel is slowing at a rate of 5 radians per second, what is the force of friction between the wheel and the axle? So guys, when we're faced with a word problem, the first thing we need to do is go through and identify all the quantities that we are being given. So the first quantity here is this 10. What is this?
The inertia.
Yeah, that's that capital I. That's the moment of inertia. And then, what is this?
That's our,
Yes, angular acceleration. And that's important because that means that this object is accelerating. The torques do not balance. When the torques are not balanced, you have to use Newton's second law. And then what we're being asked to find is the force of friction. And so I actually am going to need two equations to solve this. I can't solve it with a single equation.
Tom.
Can anybody identify one of the two equations I need to solve this?
Yeah.
I'm going to need Newton's second law, guys. If there is a net torque, you're probably going to have to use Newton's second law. And so Newton's second law says alpha equals net torque divided by I. And then I'm going to need another equation. Anybody think of the second equation that I might need?
The equation
Kinematics.
fixed.
Yes, Rachel got it. It's torque, in this case, is the radius times the force. I guess technically times the sine of the angle between the radius and the force. But in this case, if you look, guys, it's the axle. Right? There's a force of friction tangent to the axle. And so it's already at a 90-degree angle. And so the sine is just going to be 1. There's no other forces causing a torque on this wheel. So those are the two equations that I need. And so I got to combine those. And so I'm going to get alpha equals R times force friction divided by I. So then I can rearrange that a little. I can multiply each side by I, and I can divide by R, and I get alpha times I divided by R equals the force of friction. And guys, this exact problem is in your practice assignment that goes with these notes. Well, a similar problem. It's not identical, but it's pretty much the same. You're going to use a similar approach. Alpha is 5. Moment of inertia is 10. And the radius is 0.01. So that's equal to 5,000 joules. Guys, this might be, in terms of linear motion, this would be the same as I told you something's acceleration as it was sliding along the ground, and I asked you what the force of friction was as it was sliding.
That would be mean.
But that's the same problem. You do the exact same steps, just instead of torque, you would write that the force is equal to the force of friction. So you have acceleration equals force of friction divided by I, or divided by M. Let's do another example. This one's harder. This came from a AP multiple choice question. It says a disk with a radius of 0.5 meters is free to rotate around its center without friction. A string wrapped around the disk is pulled, exerting a 2 Newton force tangent to the edge of the disk for 1 second. What is the rotational inertia of the disk if it rotates through an angle of 6 radians in this time? So again, I gotta go through this and identify everything that I'm being given. I'm being asked to find the rotational inertia, right? What is I? That's what I'm being asked to find. What is this quantity here? What variable is that? Theta. It's either theta or delta theta. Can anybody tell me when theta final and delta theta are the same? Under what circumstances are theta final and delta theta the same?
When the initial theta is 0.
Yes, when the initial theta is 0. And so you get to choose what the reference line is, so you can always set the initial theta to 0. So these are interchangeable. And then we're given a force and we're given a radius. Why do you guys think we're given a force and a radius? Yes, this is probably going to be useful for computing torque. Oh, and we're also given a time. 1 second. So again, I'm going to need two equations. What's one equation you guys think I need here?
The torque equation.
Yeah, I'm going to need Newton's second law, right? So alpha equals torque net divided by I, that's 1. What do you think the other equation I need is? So somebody told me just now, I have the information I need to get the torque. That's the force and the radius. So I think it was one of you guys over here, you said torque is equal to force times radius. I actually need a third equation here. The second kinematic equation, theta equals 1/2 alpha t squared. So I need 3 equations to solve this problem. So I'm going to use the second kinematic equation. Step 1, I'm going to find alpha. I've got theta equals 1/2 alpha t squared, which means that alpha equals 2 theta divided by t squared, which equals 2 times the 6 radians divided by 1 second squared, which is 12 radians per second squared. Step 2, I need to find the torque. And the torque is just equal to the force times the radius at which it's applied, which is 2 newtons. And it's applied at a radius of 0.5 meters. That is 1 Newton meter of torque. And then put it all together. So I is going to be equal to torque divided by alpha, which is 1 divided by 12. Guys, notice here that you're going to see this situation a lot, where this is something the College Board really likes, and I would say just physics teachers and physics professors in general really like this, where you have a wheel and there's like a string wrapped around it pulling on the edge, creating torque. And so you'll see this a lot. It's essentially the same as if I was rolling this wheel along the desk, and so I had a friction force along the edge causing it to speed up or slow down. It's the same idea. All right, so now yeah.
For the first portion of that, just so I'm clear, the 2 theta is coming from The fact that you have to multiply the denominator to the theta, right?
Correct, I multiplied each side by 2, so that 1/2 times 2 would cancel. And so I had 2 theta, and then I had to divide across by t squared. All right, so now, guys, the big question is, okay, so this is great. We can determine the rotational inertia of something in this kind of roundabout way. This is a very experimental way of determining the rotational inertia, but is there an easier or a more direct way? What determines I? In other words, what properties of an object determine the rotational inertia?
The force.
So I want you guys to tell me what changes do you guys think I could make to this wheel that would make it harder to rotate?
Make it really small.
The radius.
Make it smaller and heavier? Why would making it smaller make it harder to rotate?
Because you have less torque.
Oh, okay. Assume that I'm a magical person. That's not much of an assumption. I'm a magical person and I can apply exactly as much torque as I want, regardless of the radius. So assuming I could apply any amount of torque that I wanted, what changes to the properties of this wheel would make it harder to rotate, assuming that I could apply whatever torque I wanted?
Density?
What's changing gravity effect?
Unequal mass, like sticking something.
Like putting masses on the spokes?
Yeah.
Why would that make it harder to rotate, you think?
Because the mass is all over the place.
Okay, interesting. So you're saying it matters where the mass is located. Interesting. What else could I do to this wheel? He's saying that I could change where the mass is. So I could put masses on the spokes to kind of just change where the mass is located. What other changes could I make? This wheel's not very massive. Actually, this wheel is super massive. This is quite impressive what you guys are witnessing right now. But what changes could I make that might make it harder to rotate, I wonder?
Mass.
I can increase the mass. Oh, interesting. I wonder how you got that. Guys, there's 2 properties that determine how difficult something is to rotate. The first one is the mass of the object. A more massive object is harder to rotate than a less massive object. Imagine if this wheel was made out of solid steel. This wasn't rubber, it was made out of solid steel. It'd be a lot harder to rotate, right? A more massive object is harder to rotate. But then, that can't be all there is to it, because I said there's a rotational version of mass. And if the rotational version of mass is just mass, then it's not a rotational thing at all, it's just mass. And so you are 100% correct with what you said. It's where the mass is located that matters. It's how the mass is distributed on the object. If you put masses closer to the center, the object will be easier to rotate. If you put the mass far from the center or far from the rotational axis, the object will be harder to rotate. And you guys know this. You've taken advantage of this before, probably without realizing it. Have any of you guys ever tried to like balance a broom on your hand?
Yes.
Yes? Do you balance it with the bristles down on your hand or with the bristles up?
The bristles up.
Is it easier to do with the bristles up, or are you just doing it for sanitary because you don't want to touch the bristles?
Easier.
It's easier. So let's think about why it's easier. Because the mass of the broom isn't changing. If I hold the broom this way versus if I hold it this way, the mass doesn't change. Mass of the broom is the same. But you're saying that if I hold it, let's say that this mass is the bristles, and I'm going to connect to the mass, and you're saying that this is harder to balance than if I put the mass at the top and balance it. And so let's think about why that is. Because if I try to balance this on my hand, and I can do it, I'm very talented, it's not too difficult, but watch what happens if this starts to tilt. Okay, watch what happens if the stick starts to tilt, which is what I don't want. I don't want it to tilt. It starts to go really fast, right? That's because gravity produces a torque, which causes it to start rotating, right? So as soon as it starts to tilt, gravity creates a torque, and then it starts to rotate really fast. wouldn't it be easier for me to catch it and balance it again if when it started to rotate, it was rotating really slowly? So I can't control the torque that gravity creates, but I can control how fast this rotates with that torque. When I've got this mass at the end, if it starts to tilt, gravity will create a torque, and it starts to rotate, but look how easy it is for me to catch it. The rotation is much slower, so I can catch it easier. So it's easier to balance when there's more mass at the end, because I am increasing the rotational inertia by putting the mass at the far end. That's why when you balance things, you want to balance them with the heavy end up. Because you want to increase the rotational inertia. You want to increase how far from the axis of rotation the mass is located. One really important point, guys, that I cannot stress is it's so important. An object can be rotated around multiple axes. Each axis that you rotate it around has its own rotational inertia. Guys, look, if I take a pin, I can rotate it like this, right? That is very easy to do. All of the mass, my rotational axis runs straight down the core of the pin. And it's very easy to rotate because the mass is very close to the axis. But I can also rotate the pin like this, around its center, around a point in its center. Let me use the meter stick to make that more obvious. I can rotate it around the center. And in that case, if I'm using the meter stick, I have half of the mass on this side is within 50 centimeters of the rotational axis. And then the mass on this side is also within 50 centimeters of my rotational axis. So it's farther away than if I was rotating the meter stick like this. Or I can rotate the meter stick around the end. And now all the mass is really far away from the rotational axis. So the same meter stick can have a different moment of inertia or a different rotational inertia depending on the axis. The same object can have more than one rotational inertia. It depends on your axis. So guys, I want you to remember this. If I ever ask you, for example, I say, tell me what the rotational inertia of this meter stick is. You need to ask a follow-up question. What's the follow-up question? Well, you know where the center of mass is. Where's the axis, right? Yes. Where is the axis? Which axis are you talking about? One through the center? Are you talking about around this end? Do you want me to rotate it around a line that runs all the way through it? Which axis are you talking about? Because they all have a different moment of inertia. Right? I mean, I could take a drill and drill a hole anywhere on this that I want to, and then put a pivot through it and rotate it around that point. Every point is going to have a different rotational inertia. It's the same thing with the wheel, right? Guys, generally speaking, you rotate a wheel like this, right? But I don't have to do that. Watch this. I don't have to rotate it around this axis through the center. I can also rotate a wheel like this. That's going to have a different moment of inertia. That's a different axis, right? I could even, guys, I could hinge this right here and rotate it around this point and make a little pendulum. That's going to have a different moment of inertia as well.
Yeah.
Oh, if you guys are interested in that, take AP Physics C and we will do pendulums that look like that. It's a lot of fun. It's called a physical pendulum. So a quick check. Guys, a ring and a disc. I wonder where I've seen that before. A ring and a disc of equal radii and equal mass are rotated around an axis through the center. Which object has a greater rotational inertia? Why the ring, Mary?
Because all the mass is a farther distance.
All of the mass, guys, these two objects have the same mass. But for the ring, all of the mass, if this is my axis of rotation, right here in the center, all of the mass is far away. For the disc, some of the mass is far away, but some of it's really close. So the ring has a greater rotational inertia. And guys, remember what that means. That means the ring has a greater resistance to being rotated. The ring does not like to be rotated. The disc doesn't mind so much. The disc is not as resistant. So does it make sense why the disc wins the race?
Yes.
The disc is less resistant to rolling. It's less resistant to being rotated around its axis. So it wins the race. Same mass, same shape, but they have a different moment of inertia. So based on that, now guys, this is a slightly more challenging problem, but I think you guys will get it. Two spring scales are each attached to a cord that is wrapped around a pulley. The two pulleys have identical mass and radius. The pulleys are initially at rest when the two spring scales are pulled with the same constant force, causing both of the pulleys to rotate. Which of the pulleys, if either, will complete one revolution first? Is it pulley A, which is like a ring? Is it pulley B, which is like a solid disc?
Oh, you got it.
Or will they complete one revolution in the same amount of time? What do you guys think? 1, 2, or 3?
You said A is the solid disk?
Yeah, A is the solid disc. So A is a solid disc, B is a ring. Or does it matter at all? They both rotate the same. All right, I see an awful lot of people choosing pulley A. Now, guys, the correct answer is A.
Okay, thank God.
Can somebody explain why? Can somebody tell me why? Go for it.
I'm assuming the spring scale applies the same torque to both the wheels.
Yes.
But since the pulley B, all the weight of the pulley is distributed to the outside, it has a greater rotational inertia. So pulley A would rotate or complete revolution first.
Excellent, good. I'm really glad that you said, that you mentioned the fact that they both have the same torque, because that's important. Same torque, but this one has a greater inertia, so it has a lower angular acceleration. Exactly. So the pulley A rotates easier, so it's going to spin around faster. And guys, by the way, this came from an FRQ, so this was like half of an FRQ, which you guys just argued right there. Guys, you need to memorize these. You got to memorize this diagram. No, I'm kidding. You don't have to memorize it. It says at the bottom. You do not need to remember these formulas. Guys, these will be given to you if you ever need to use them. You don't need to write these down. You don't need to take a picture of it. I'm showing this to you so we can discuss it. You don't need to remember it. I want you guys to see these formulas, but again, they will be provided to you if you need them on any problem. And if you ever need them in the real world, you can look them up on, there's a million websites, or in any physics textbook, you'll find the same thing. But I want you guys to look at a couple of important things. First off, guys, notice that we have a cylinder. Actually, let me go to the easiest shape. This is just a rod or a stick. Notice that it appears twice on this table. Once if you rotate it around an axis that goes right through the middle, and once if you rotate it around an axis that goes through the end. Which of these two moments, which of these two eyes is a bigger number?
The top one. Or the
bottom.
Yeah, the bottom one. 1/3 is a bigger number than 1/12. In fact, this is 4/12, right? This is a bigger moment of inertia if you rotate this stick around the end versus if you rotate it around the middle. It's a bigger moment of inertia. So that's the first thing. Notice that the same shape has multiple moments of inertia, depending on your axis. And then the second thing to notice is that all of these formulas kind of look similar, don't they? They're all some fraction multiplied by the mass of the object times either the radius or the length squared. So they all look very similar. Really, the only difference is this fraction, right? So the important takeaway is the moment of inertia for any object depends on the mass of the object, and then it also depends on the size of the object. If the sphere had a bigger radius, then I would be bigger. But notice, guys, which is more important? Is it the mass or is it the size? Which one is more important in this formula? The mass or the radius of the sphere? Yeah, because it's squared. Doubling the radius gives you 4 times the moment of inertia. Doubling the mass just gives you double the moment of inertia. Okay, so again, qualitatively, I want you guys to understand these numbers, but you don't need to remember these formulas. You will be given them if you want to need them. And then the very last thing I want to bring up here, we're almost out of time, and that is rolling. Guys, in order for an object to roll, there has to be friction. You will never be asked to calculate how much friction, or you will, in fact, never be asked to do any kind of a calculation involving an object that is rolling. But you guys do need to know that in order for something to roll, there has to be friction. Can anybody, looking just at this diagram, can anybody figure out why? Just based on this diagram, can anybody see why an object that's rolling has to have a friction force to start rolling?
Because otherwise there's nothing to really roll against.
Okay, I think we're going. What do you guys think?
There's no other horizontal binding on the object.
Ooh, okay, I think I see where you're going with that.
It's not gonna exert torque because it's just gonna be like gliding along.
Yes, okay, exactly. Guys, without a friction force, ignore the friction, do either of these other two forces create a torque? The
You
normal
got it.
force doesn't create a torque, it's in the wrong direction. Gravity runs through the center, so it doesn't create a torque. The only possible torque would be from friction. And so if a thing isn't rotating to begin with, it won't start rotating without friction. It won't start rolling. That's why, has anybody ever played pool?
Axis of rotation.
Guys, if you hit the dead center of the cue ball, it doesn't start spinning, right? You just hit the dead center, it starts to slide. But as it slides, there's friction, and that friction makes it start to roll. So even if you hit the dead center, it doesn't start spinning from your cue state, but it will start spinning because of friction. And so, just make sure that you understand. I put a link to a little simulation you can play around with to kind of see it in action. But the normal force doesn't create a torque, so that can't start something spinning. Gravity always acts at the center of mass. Gravity can't create a torque here, so it's not going to cause it to start rolling. Friction is the only force that can create a torque that makes something roll.
Friction forces perpendicular to the axis.
There you go.
If this surface was frictionless and I put the wheel and the disc and the ring on it, they wouldn't roll down it, they just slide down it.
No rotation.
Wheel slide down.